Okay, so the first talk given by Shaptaki has already introduced LHC. I just have a couple of slides to get you oriented again. So we found the Higgs, and this is a picture of the colloquium that was given on the day of the discovery. And since then we have been interested in this boson and have been testing various properties, and not only of the standard model Higgs but also of the various other theories which are beyond the standard model. And I'll just talk a little about two of those searches. So this one I guess everybody has seen at some talk or the other. So this is our experiment CMS, in which Indian universities and institutes collaborate. That's why we always show the CMS results in more detail than the our across the ring competitor Atlas. And you have also heard something about it, I see in the agenda. So this is just to give you a brief description. All the experimentalists of course know this, but just to show that you know, if I take this to be the collision axis, the beam axis, then I can say that this is the z direction, and this I can take as the y direction. It is symmetric in x and y, of course. And our detector really looks like this. This is a slice of that. So we have the tracker right next to the collision point, and then come the calorimeters. There are two different types for electromagnetic and hadronic activities, and the whole thing is enclosed in a magnetic volume, which basically serves the purpose of momentum measurement in the tracker. And at the end, we have these penetrating particles, which are the muons, which go through everything, and that's why we put detectors to detect these particles at the very end. And of course, these return yokes in CMS also create a magnetic field in this volume, which helps us track the muons. So this is just a cross-section view of the same detector, say the XY view, and you can see the same thing. The electrons are detected in the electromagnetic calorimeter, and then the hadrons, and then this is the magnetic solenoidal section, which creates the field here, and then last is the muon chamber. So this already has been shown by Shaptaki, so I will not show that. And then I just have a very simple slide to tell you the difficulty in constructing these various elements in our experiments. And we start here. So the initial things that we of course measure are the energy, the momentum, and do some particle identification, and of course measure the missing energy that is there in our detector after every collision. And from that we can identify these particles, the electrons, muons, photons, and this of course denotes the neutrals. And then the difficulty level increases as we go and, you know, reconstruct more and more composite particles. So after this line comes the various mesons and the baryons, the pi and the k and the lambda, etc. And then even more, you know, heavier and difficult to detect particles. So the tau lepton, on which, you know, the two searches that I'm going to describe is based, is somewhere in between. It is a elementary particle, so it is just the next lepton to electron and muon, but at the same time it is heavy enough that it decays very fast, and so I have to reconstruct this particle from its decay products. It is not just simply one detector like the electron or the muon which can detect this particle, so it is a bit more difficult. And then of course the bottom quarks and the mesons, and then the top quarks, which are detected in this order of difficulty. And then of course we go to you know, much more sophisticated searches. We search for supersymmetric particles and Higgs, etc. So this just will give you a glimpse of the difficulty that we have at LHC or at any collider experiment, but at LHC the difficulty increases. So okay, so here is some data on the collision section, so which is like about 5.5 centimeter in Z direction, and in the cross section 15 micron versus 15 micron, and these are some data on, you know, the energy is of course now 6.5 TeV, and something on the luminosity, which is the number of collisions per unit time per unit area, which is very important for us, because the more we have, the more rarer kind of physics we can study. And just to tell you that the beam in LHC comes in bunches, so we always show these bunches. They have got some specific length and some cross section, which I already told you here. And just to give you an idea of the rate, so the bunch crossing is about 1.5 into 10 to the power 7 in 1 second. There are many protons in a bunch, so the number of proton collisions is 4.5 into 10 to the power 8 in a second. And of course, then when I go to my new physics, Higgs, SUSY production, etc., that is roughly of the order of 1 in 10 seconds. So I just want you to note these two numbers and see that how difficult it is and how rare it is for anything new and exciting to be produced at LHC, even with the very high energy and high luminosity. So of course I should apologize, these numbers may change slightly depending on the current luminosity and the energy. So the other difficulty we have, because as I showed you, there are many protons in a bunch and the bunches cross each other and there are collisions. So as a result, in one particular bunch crossing, we have this many number of interactions, which is really, really large. So, but I have to find out which of these collisions is of interest to me and really, map out all my physics with respect to that particular vertex. So each of these interaction points is called a vertex or the event vertex or the primary vertex. There are many names. And this has to be very precisely determined, otherwise the physics does not stand up. So that is the problem. Okay. So these are the tough things that we have to face in LHC. Now the analysis strategy. All this stuff is more or less general for every analysis that we go through, and slowly we will come to the tau analysis. So what happens is, after we collide these proton versus proton beams at LHC, there is my detector sitting here. And after the data is collected, it has to be passed through something called the trigger condition. So I really have to throw out a lot of those collisions which are not of interest to me, and I have to pick out the ones that are really good and I want to study them further. So after this part is done, we go through digitization. That means the data is, changed into a certain format for easy access and easy computation later on. And then comes what is called the reconstruction, where the digital data is made into tracks and particles and energy and missing energy, everything that I listed before. So after all this stuff is done, this is on the experimental data side. I have some kind of loose selection on the data so that I need to, even after all this trigger condition, etc., I still need to throw away a lot of the data because some detector or something, some condition was not very ideal and I don't want that data. So that is what is good event selection or good run selection. So, and on the other side, I have to simulate a lot of my data, you will see later on in the later slides. And that simulation has to go through the exact chain like the, the experimental data. So what has to happen is, I have to generate that using some Monte Carlo generator, which is not a very easy thing. There are new generators coming up constantly so that they can simulate this collision and the physics that follows better. And after the initial physics input, the process called hadronization happens, which basically changes the parton level stuff into normal particle level stuff which we can observe. And then there is again the same thing, like first the detector effects are added, because I can hadronize, but I will not know what happens when the same particles pass through my detector. So those detector effects have to be incorporated, and then of course same reconstruction, it is exactly the same here. And then this set of data have to again go through some very high level trigger selection so that we can throw away more data. And then of course the event vertex, which I just now talked about, has to be reconstructed properly. And then after I get my event, one event is one collision basically. So after I get that collision, select that collision, I also have to make sure that the original trigger condition that I had thought about really does exist in my event. So I do this trigger matching. And of course, also in the simulated part, I have to do generator level matching. Whatever happened in the parton level should also match after my reconstruction. And then this analysis strategy basically develops. I categorize the events, you will see, in many different categories, which is beneficial for me to do further selection. And then of course, Shataki has already talked about the statistical interpretation, which is battery is probably. Okay, so the statistical interpretation of the data, which gives my final results accordingly, whether I found the particle or whether I am going to set limits on some of the cross section, that is the production probability and masses and stuff like that. So that is the end thing, the results. So I am going to talk about these two things: production of the MSSM Higgs bosons and production of two Higgs bosons together. These are the two things we studied recently. So the MSSM Higgs bosons, of course, there are these two different modes of production, and in this production of two Higgs bosons, they are both standard model Higgs, and we studied this channel where one Higgs goes to 2 d quarks and the other goes to 2 tau leptons. And I forgot to mention here, in the MSSM case, the Higgs actually decays to 2 tau leptons. So that is why the tau is the theme of this talk ultimately. So actually, before I go on, I should just mention why is tau important, because of course, as you see, the Higgs can decay to many other things, the tau tau, BB, WW, many other modes. This tau tau mode is very important in the sense that it has got one of the higher branching ratios compared to the other Higgs decays. So of course, BB is much more, and the WW follows, but it is more difficult to detect these modes, and because the BB has got a huge background and so does the WW. In that sense, tau tau is very unique, because once we have invested time and methods into finding the tau properly, then the backgrounds really go down, and I can detect this Higgs to tau tau very more easily than the other modes. So that is the importance of this channel. Okay, so I should spend a little more time in this di-Higgs modes, because I did not show any in the previous slide. So in this mode, what happens is, these are the, so there can be a standard model production, there are these two figures which compete with each other, and as a result, the final cross section is actually very, very small for standard model di-Higgs production. It is about 10 femtobarn at 8 TeV. So, so what happens is, because of that, we don't detect these modes just like that. I mean, till now we have not detected, but these modes, I mean, if we can go anywhere near the standard model cross section in my measurement, then actually I would be able to probe the trilinear Higgs coupling from this, as you can see from this Feynman diagram. Okay, so but also there are other BSM theories which present, which predict the enhancement of this di-Higgs cross section up to 1 picobarn. So from 10 femtobarn, we can go up to 1 picobarn due to the decay of exotic particles, for example, the spin 0 radion or the spin 2 graviton. So there are many theories which predict this. So one of the main things that we have followed is this extra dimensions. So, and this is the reference, the paper from which we have, we have studied and we have started this search. So I think this battery is gone. So, so the leading order Feynman diagram for the resonance search is given by this second Feynman diagram here, and so we have searched for both these cases, the non-resonant as well as the resonant channel. So, yeah, this is not working. The forwarding is okay, yeah. So before going on any further, I must talk about the backgrounds that contribute to these channels. So you people know about these, what the word background means. So they basically show the same kind of signature as the the signal. So here there are various of these backgrounds. So what I am showing here is a plot where the x-axis is the mass of the 2 tau system, okay, and on the y-axis, of course, it's the number of events per mass bin, which is a GeV here. So there can be several of them. So let's go to this one. So Z going to 2 taus. So this is of course very similar to Higgs going to 2 taus. So of course this forms a very big background here, and this we have followed a special technique to get this background, which is really unique. What we have done is, it is not easy to find and determine the taus because they have got neutrinos. So that is one difficulty in the tau search. So what we have done is we have taken something called a embedded sample. So we take the z going to 2 muons, mu plus mu minus data events just from data, normal experimental data, and these muons are really replaced by the taus from simulation. So the taus we get from simulation, and we replace the mu's in the data with the taus, and then it makes a z going to 2 tau simulation sample for us, where the rest of the kinematics of the event is actually very well modeled because we are taking it directly from data. So this is a specialty of this particular Higgs searches. So the other type of background could be the electroweak background, which is W plus jets or the diboson. So they are obtained by different methods. For example, the W plus jets, the shape of this m tau tau distribution is obtained from simulation, but the yield, how many we get for a particular luminosity, which is 18.3 femto1 inverse in our case, we obtain from a data which is rich in the W bosons, that is the high transverse mass region in data itself. So I can just get the normalization very accurately. So the diboson signal also we estimate, but we do it completely from simulation because this is a very small, it is working sometimes. Okay, so similarly TT bar also forms a background, and why all these things form backgrounds here? Because they all can decay to tau leptons, and so that is the reason we have to simulate or estimate them. So we get the estimation of the TT bar backgrounds from again from high purity region means region where the TT bar purity is high, from the E mu decay channel. So where the one of the T goes to electron and the other one goes to muon plus some associated jets. So we get it from there. So the standard model Higgs in all these channels, the associated production with Z, with W, with QQ, gluon Higgs, and Higgs going to BB bar. They all Higgs going to BB bar, of course, is a background in the Higgs going to tau tau search, but not in the di-Higgs search. So all these also form a background, and you can see it here in this green one. And of course, the QCD multi-jets, they are everywhere, and they also form a background here, and one of the largest backgrounds. So what I have done in this plot is, I am plotting the mass of the tau tau system for all these samples, and I am just stacking them up. So I am plotting one after the other. So some of them are not very visible because they are sitting on top of the larger ones. And but they are all there here. So this is the story of the backgrounds. Now, so the next thing I should describe before I go on is how we identify and reconstruct the hadronic taus. So Shattoki actually gave an introduction to this in the beginning in his talk. So the slide is I think more or less the same. He has described it. So let me just quickly go through it again. So one thing you notice is these are the various decay modes of the tau leptons, and the hadronic decays where the taus go to hadrons, they are the largest fraction here, and the others are actually much smaller compared to this. So that is why the hadronic mode is also actually very good for us, because we can get a lot of the data here. So what we have, what I mean by the hadronic decays is this. So it is basically drawn here. So it is the pi plus hadrons, pi plus or pi minus, and the pi zeros associated with it. Okay. So I have to, right now my categorization starts. So I am dividing the sample into 3 different cases. One in which there is only a single prong or track or charge track or whatever. And the second one, there is a single charge track plus 1 pi 0. And the third one is 1 prong and 2 pi zeros, and then I have a 3 prong, that is 3 charge tracks category. Okay, so these are actually done by this hadrons plus strip algorithm in CMS, which basically reconstructs the hadron, that is the track, and then finds a strip in the electromagnetic calorimeter, which denotes the pi 0. So, and this really helps in reducing the jet to tau fate rate. So basically this hadronic tau is like a jet. Jet means a stream of particles from any source. So this is a big problem in this kind of analysis, because the tau jet is often faked by jets that are not taus. So this is a problem. So the tau ID efficiency, the identification of the taus, the efficiency is about 60% for taus from 20 GeV to 2 TeV. So you see how large this range is, but CMS does a good job and has a good efficiency throughout this range. And the fakes, which are, the jet faking a tau, or a electron faking a tau, or a muon faking a tau, all this is possible, but these fake rates are very small. They are of the order of 0.1%. Okay, so the taus are also required to satisfy the isolation criteria, because these are prompt, very fast tau hadrons, and they should not be associated with a lot of energy around them. And we have to require the absence of hadronic activity in their immediate vicinity. Okay, so this is one more condition that is really needed. And this also, is described many places. It's very simple. So this is the tau direction. I draw a cone around it. So the cone is of the delta r. So this distance in eta phi plane is is r equal to 0.5. And so what I do is, EF is always particle flow reconstructed. What is particle flow that Shataki has mentioned? We involve all the detectors to find the particles. So the PT sum input of all elements bigger than 0.5 GeV, so I don't consider the very, very low energy stuff. So, and the photons with ET greater than 0.5 within, so delta Z of 2 millimeter from the production vertex. So there is a cut here also, there is a selection here, and within a cone of delta R less than 0.5. So this has to be computed. And then, I put several criteria on this particular quantity. So the production vertex, of course, has to be denoted first. So this has the highest probability of association with the leading or the highest PT track of the tau candidate. So whichever is my tau candidate, generally the highest PT of those, I mean the fastest tau, that has to be associated with a particular vertex, and that is what I call the production vertex, and I map out rest of my physics with reference to that particular point in the detector. So, so the hadrons and photons forming the tau candidate, of course, are excluded from this sum. So the center is excluded, otherwise, the sum will be very big anyway. And the pile up means basically the activity due to the other interaction vertices that I showed you. They all leave tracks, they all leave energy in the event, and that extra energy has to be accounted for properly. Otherwise, also my calculations of the energy momentum of various particles will be distorted. So there are some things that I call working points. That means these are the analysis points where analysis is done. I can require the isolation to be less than 2 GeV, I can require it to be less than 1 GeV, or I can require it to be less than 0.8 GeV. So you see the cuts are becoming very, very tight as I go like this, because if I require the energy in this region to be very small, of course, those kind of taus will be much fewer than if I require the energy to be larger. Okay, so you do expect, but these are right now for this 8 TeV analysis, after a lot of optimization, these were the values that were found to be suitable. Oh, okay. No. So this is only, I should have added another point here. Usually this is the isolation energy, but we use the relative isolation. We always divide it by the energy of the central particle. So that is always done. Yeah, so that is I should have added. Okay, so the next categorization, oh, my time is actually up. Okay, I'll just take a few more minutes. So the next categorization is in terms of this B tag and no B tag. So this is especially for the MSSM search, you need this, because again, I can require B-jets in the event which are good for this kind of mode, and I can require no B-jets to be in the event. I mean, basically I don't require anything on the B-jet criteria, and then this mode is picked up by this kind of events. Okay, so we basically have to reduce this QCD multi-jet background, and for that we have optimized the tau PT, both the leading and the subleading. for both these categories, just to see where they do which values they do a good job for. So here is a plot which shows this if I increase the selection on the tau pt, so I require the tau pt to be bigger than some quantity. So the tau 1 pt means the leading tau or the highest pt tau in the event. So how the background actually reduces. So here my QCD is much less than what it was here. And of course the total number of events also reduces, you have to remember. So I am also losing signal. But the rate at which I lose signal is less than the rate at which I lose background. So that is the idea. So after that what I have to do is, so these are various kinematic variables I am showing. So the PT of the tau, first tau, PT of the second tau, these are all cut out. So this is the missing energy. This is the visible mass of the tau. There is a special technique which I use to include the neutrinos. And then this is actually the whole system of the tau, the mass again, not only the visible part. And this is the Higgs PT, which I calculate and plot. So the object of this plot is to see how well my data is matching my background prediction. So the background is stacked up here, and the final these dots with error bars are the data. So if they match well, that means my background computation or selection or simulation, whatever I have simulated in the background, it is done well, the job is done well, and they match. Because of course the Higgs signal is not large here, so mostly my data is going to match my background. So, so here I just want to show you one plot. Actually, this one is better. So this is showing the, I think this was the QCD, multi-jet events. Okay, so yeah, the multi-jets. Okay, so here what I am showing is on x-axis it is the invariant mass of the two taus of the tau system, and the plot is made by different groups, and we have to synchronize, and each has to match the other. And this is the level of synchronization. So I have just taken the difference. So this plot doesn't look too good because visibly they look different, but we had to reduce this difference by less than 5%. So all my points had to be between this, this bar here. So this went on for several months actually, and only when this was satisfactory to the Higgs group, we could proceed with the rest of the analysis, and we could give our final results. So it is quite tough. So here actually this is the same thing as the figures. So it is different backgrounds. The total expected background is here, and the observed data is here, and these are the signal values, but they are quite small. So you see that roughly the expected background yield matches the data. So for different categories and different tau momentum. So that's why there are so many values. So I'll just come to the result because I wanted to give you a flavor of what is done in the analysis. So the results are not, you can get them anywhere. So this is for the MSSM Higgs. So here standard model Higgs is treated as a background, and these are the two different modes I have shown. So if I look at the gluon fusion mode, I am taking the B associated production as a nuisance parameter in the maximum likelihood fit, which is called profiling, and what this is, this also Shakti has mentioned in his talk, and the other way around. So if I take the B associated production limits, that is this one, then I take the gluon fusion as a nuisance parameter. So this is as the limit of mass versus cross section, since we did not find any signal. Okay, so and here there are the two limit plots for the two resonant cases, spin 0 and spin 2, and done in the same way. So this is the mass of the resonance, and this is the production cross section times branch interaction. Okay, so I will end my talk. There is time is also up. I just wanted to show this picture to tell you that this is a picture of the LHC computing grid. And this analysis that we have done till now and what we are doing in future would not have been possible if this grid system, which is very new to the world, now people are slowly adopting it, but it was done first for LHC experiments. And you see 2 points here in India. We have 2 grid centers, one is at TIFR. So without this heavy computing possible in a parallel system, we would not have produced those results. And of course, I wanted to show that in this, the numbers have increased now. 3,600 physicists and 38 countries has increased, and 182 institutions roughly. India is not a very small part of it. It is actually quite